Following is a class on carbonyl compounds, aldehydes and ketones. So, there are many carbonyl compounds, and the basic carbonyl compounds are aldehydes and ketones. Then you have carboxylic acids, acid chlorides and derivatives. Okay? So, carbonyl compounds have its C double bond O group. Okay? And aldehydes and ketones are functional isomers of each other. That means a compound having the same formula can be an aldehyde or a ketone depending upon the location of the C double bond O group. Coming to the general formula. CnH2nO is the general formula for aldehydes and ketones. Now, CnH2nO is the general formula for a monoaldehyde and a monoketone. So, if the number of CO groups increase, accordingly the formula changes. But this is for monoaldehydes and monoketones. Okay? Now, aldehyde. Structurally, it's R, where R is an alkyl group or an alkynyl group or an alkenyl group. Okay? So, if this C double bond O is the term, this carbon affixes the terminal carbon, that is, if this carbon is attached to an hydrogen and an alkyl group, and this being the terminal carbon atom of a carbon chain containing the C double bond O group, then it's an aldehyde. Whereas if this carbon atom containing the C double bond O group, the carbonyl group, is not in the terminal position, that is, it's in between, middle of the carbon chain, then it's a ketone. You have two R dash groups where these are alkyl groups. Okay? Now a special case. Basically, HCHO is called formaldehyde. It's the first member of the aldehyde series. Here also the carbon atom is terminal, but no R group is attached. So this is also an aldehyde because one carbon atom, which is the terminal one, formaldehyde. Other all aldehydes have an R group attached. So these are things. Okay. What are other functional isomers? You have unsaturated alcohols, cyclic ethers, and aldehydes and ketones can be functional isomers of each other. Okay? So that was a brief introduction. I'll be basically discussing the physical properties, chemical properties and methods of preparation of aldehydes and ketones. There are some methods which are generic for both aldehydes and ketones, whereas a few methods are specific for aldehydes only and others for ketones. So, let's start methods of preparation. I would like to more deal with mechanisms as far as possible within the scope of IIT syllabus, and in some cases I'll only be teaching you the method how you get the answer. Okay, and in some cases we'll directly get to the answer without just by remembering it. So methods of preparation of aldehydes and ketones. From a very old friend, alcohols. If I treat with a mild oxidizing agent, what happens? Let's see. You have an alcohol. Let me purposefully take this alcohol, and you treat it with PCC. PCC is pyridinium chlorochromate, which is C5H5NH plus CrO3Cl minus, and then you get your aldehyde or ketone. Okay, you see PCC is a very mild oxidizing agent. If you use a very strong oxidizing agent, you may get all the way to carboxylic acid. So the PCC doesn't affect the olefinic group, that is the CC double bond. So only the alcohol is oxidized to aldehyde or ketone. PCC is C5H5NH plus CrO3Cl minus pyridinium chlorochromate. The mechanism part, you have RCH2OH with so you see CrO3Cl minus in the presence of, I'm sorry, you have to use dimethyl dichloride CH2Cl2. You will get this kind of H2Cr O4. This acid is formed, and this is an acid, this is an alcohol. So you have esterification reaction. So by esterification reaction, you will get an ester, that is RCH2O Cr double bond O OH double bond O. So this is the ester that is formed. This is a chromate ester. This is a chromate ester that is formed. Now this chromate ester disintegrates to give rise to RCHO plus loss of a proton plus you have HCrO3 minus. So basically what is formed? Initial mechanism of this particular oxidation involves formation of the chromate ester. Acid plus alcohol forms ester, chromate ester, and the loss of a proton along with removal of HCrO3 to give your aldehyde. Okay? So if you use a ketone, you will get a ketone. So that's basically the thing. Loss of proton, second step. First step, formation of the chromate ester. Next, I will be going for catalytic dehydrogenation. This is also oxidation, because dehydrogenation is nothing but removal of oxygen. So this is already an easy thing. So if you use a primary alcohol, let's say CH3, CH2OH, and if you treat with copper at 300 degrees Celsius, you get an aldehyde, CH3CHO, acetaldehyde plus water. If you use a secondary alcohol, let's say CH3, CH3OH in presence of copper and 300 degrees Celsius, you get what you call as acetone plus water molecule. But remember that if you use a tertiary alcohol in this particular reaction, that is dehydrogenation, writing it here, if you use a tertiary alcohol, that is CH3, CH3, CH3OH, this is a tertiary alcohol, it will go all the way to form alkene by elimination. So in all this case, you have hydrogen atom which can be removed. For this, you have this and this hydrogen atoms which can be removed. Here also you have two hydrogen atoms for removal. In this case, this carbon has no hydrogen atom for removing. Since there is no hydrogen atom, only way by which this can proceed is by elimination. So it eliminates to give an alkene. So remember, tertiary alcohols eliminates to give alkene in the presence of copper at 300 degrees Celsius. So this reaction can be treated as a test for carbonyl compounds, because primary and secondary give carbonyl compounds which can be subjected to their original test to find out the answer, and tertiary alcohol gives elimination. So that was from mild oxidizing agents and catalytic dehydrogenation. Next one that we are going to learn is from open air oxidation. First step, a secondary alcohol treated with aluminum tert-butoxide. What is tert-butoxide ion? Okay, so first let's see what a tert-butoxide ion is. Should be very confident with it. So it is CH3 size 3O tert-butoxide ion with a negative charge. So 3 times air. Okay, what happens? So what you get is tert-butyl alcohol is aluminum tert-butoxide. You get a tertiary butyl alcohol plus organometallic compound with aluminum. Okay. Now what you do is, so first the secondary alcohol is refluxed with your aluminum tert-butoxide. Now you add acetone to this particular compound. Okay. Let me write R dash for convenience. First you reflux it and add acetone. What happens when you add acetone? First of all, this reaction, let's balance it 3 times, and here also you get 3 times. That gives the balanced reaction. This is R dash, remember. So you get R dash, C double bond O. This is your ketone plus an organometallic compound of aluminum. So this is your ketone formation. So this step is nothing but an intermolecular, it's an intermolecular hydrogen transfer from, if you see, this hydride ion is transferred from here to this particular compound. So this gets a negative charge, aluminum has a positive charge, forms this complex, whereas the ketone is liberated. So that was about from alcohols. Let's see at some other methods. Let me draw the compound first and then I'll explain you. Okay, so what you have in front of you is nothing but an alcohol, which is an unsaturated alcohol. This is your alpha beta. This is your alpha beta unsaturated. Okay, your alpha beta unsaturated alcohol. What is this? This is nothing but your beta gamma. Again, it's unsaturated. This is beta gamma unsaturated alcohol. Okay. Now what happens when you treat with open air oxidation? What is the reagent? Aluminium tert-butoxide. Okay. Now OH alcohol gets converted to C11O. Here also C11O. Right? And preserving the carbon. Then for alpha beta unsaturated alcohols, it just gets converted to alpha beta unsaturated ketones without any rearrangement. See, this is a very nice conjugation. But in place of beta gamma, what it is noticed that mostly in beta gamma unsaturated alcohols, along with the formation of the ketone, a rearrangement takes to the alpha beta form because of this conjugation that is present on the C double bond O group along with the double bond. So because of this particular case, we have seen that in open air oxidation, beta gamma rearranges to alpha beta with the oxidation of the alcohol. Now that was about some typical applications. Now our next method of preparation is from fatty acids. So it's about fatty acids, and the first thing in that is by dry distillation of calcium salts. Okay, so dry distillation of calcium salts of fatty acids. Let me take calcium formate, heating, dry distillation. You get calcium carbonate plus formaldehyde. If you take calcium acetate, again dry distillation, you get calcium carbonate plus your ketone, which is, what is this? Your acetone. Now let me tell some ways how to get this. You have H, C double bond O, O, Ca, O, C double bond O, H, and when you heat it, what happens? See, these are not ionic reactions, so heating reactions are very difficult because of the free radical approach generally taking place. So let's learn how to get to the answer. In case you don't remember, what happens? Just this gets removed. Okay, C double bond O gets removed and calcium carbonate gets formed. Okay, so you get formaldehyde. Now what in case of this one? You have CH3, C double bond O, O, Ca, O, C double bond O, and CH3. Again, removal of calcium carbonate, you are left with acetone. So you see in this product, if I remove CH3, if I replace by an R group, then here we'll get R and another R. So basically we see that in this particular method we are getting only ketones, and only if H is there, that is, this is the formate salt, calcium formate, this is calcium acetate. Okay, if you use only the formate salt, you are getting only formaldehyde, not other aldehydes. But if you are using any other calcium salts, acetate, propionate, butyrate and all those, you are getting ketones. Now how to get aldehydes? So this method is not very much used for preparation of aldehydes, but let me tell you, if you use a mixture of calcium formate and calcium acetate or any other calcium salts with calcium formate, then you will get mixture of, what you will get, mixture of formaldehyde plus ketone plus aldehyde. How do you get the aldehyde in this case? You have formate let me write in this form, and here you have the other one. Okay, C double bond O R and C double bond O R. Now remove a calcium carbonate. Okay, not from here. Let me rewrite. So this removes the calcium carbonate and these two forms. So the neighboring atoms, calcium carbonate is removed, and this is nothing but your HC double bond R, which is your aldehyde. Okay. Now one more reaction. You get cyclic ketones. You get cyclic ketones when calcium salts of dibasic acids are heated by dry distillation. For example, let's take calcium succinate. So this is the salt of succinic acid. So calcium succinate. And you do dry distillation, removal of calcium carbonate, and so you get this particular ketone plus calcium carbonate. So dry distillation of calcium salts gives rise to this product. Next method, again from fatty acids, is catalytic decomposition of the fatty acids. If you take, it's similar, they're using calcium salts, here just you use the fatty acids and you get aldehydes and ketones. You use RCOH plus HCOH in the presence of either Al2O3 or MnO or THO2 at 400 degrees Celsius, and what you get, the product is your RCHO plus water plus carbon monoxide. So I saw it, it's carbon dioxide. Okay, let's take an example. If I use acetic acid with formic acid in the presence of any of the above reagents, I'll get acetaldehyde plus water plus carbon dioxide, right? Instead of formic acid, if you use Instead of formic acid, if you use both acetic acids, then you get the ketone. Basically, if you use a formic acid, then you get an aldehyde. If you don't use a formic acid, two different kinds of acids, or the same acid but a more quantity, that is double quantity, then you get right to ketones. Depending upon whether you use different acids, you get unsymmetrical ketone. If you use the same acid, double the quantity, you get symmetrical ketones. But if you use what is that? If you use formic acid, you get this. Remember, formic acid is the only acid which undergoes decomposition, or what you call decarboxylation, even in the absence of catalyst. So formaldehyde is not obtained in this particular reaction. Basically, you should be getting HCHO plus RCHO because both are getting reduced in the presence of recent reducing agent. You know, all these agents, Al2O3 or MnO, AmNO2, THO2, this all can be used as a reducing agent. So basically this should be reduced to RCHO plus HCHO. But formic acid is a not very stable acid. It undergoes decarboxylation to give water plus carbon dioxide. Next, so that was all about fatty acids. Next is hydrolysis of geminal dihalides. Okay? Remember, two atoms of other than carbon, two functional groups on the same carbon atom, geminal, and the adjacent carbon atoms, vicinal. So this is geminal, and you do hydrolases, you get rise to CH3, CH, OH, OH, this being highly unstable, two OH groups on the same carbon atom, highly unstable because of its pulling effect, which is inductive effect, and unless this carbon atom is being provided by very strong minus I group, this carbon atom being rich in electrons and it's very unstable. So what happens is this disintegrates, leading to a rise of water molecule plus your aldehyde or respective ketones. Here instead of H, if I take CH3, then I'll get rise to my acetone. Okay. So that was hydrolysis from geminal dihalides. Now we'll do a brief revision of what we learned to prepare carbonyl compounds from alkenes. So how did we make it from alkenes? Let's again do a brief revision. Here alkenes, from alkenes. So first you do nothing but your reductive ozonolysis. Okay, reductive ozonolysis. So you have alkene R, CH, double bond, CH, let me write R dash, and you treat it ozone, you'll get this ozonide. Reductive ozonolysis in presence of H2PT or Zn water in the presence of dimethyl sulfide, you get aldehydes. Okay, so this ozonide, which in the presence of reducing agent H2PT or Z in water, in the presence of dimethyl sulfide, you will get your aldehydes. Aldehydes are also formed by treating with oxidizing agents. So it's visible. Oxidizing agents containing nascent oxygen. Let us take some NaIO4. You will get aldehydes. Cut it here, and just this double bond replaced by a carbonyl group, you get aldehydes. Or okay, so no other option. And so this part will give an aldehyde and this part will give a ketone. I am sorry. Okay, because only two replaceable oxygens are there. Cut it. This will give aldehyde, this will give ketone. So that was from alkenes. Now let's go into one more form. Till now we did with alkanes, now we'll go do with alkynes. Again, alkynes basically again hydration. Remember, you'll get primarily ketones except in the case of ethyne. In this case, you'll get aldehyde. So, ethyne or acetylene is the only aldehyde which on hydrolysis gives you, it's the only alkyne which on hydrolysis gives you aldehyde. Other all aldehydes on hydrolysis gives you ketone. So I'll do it acetylene because I like it. So you treat it with water in the presence of HgSO4 in presence of sulfuric acid at 60 degrees Celsius. You get CH2, CH, OH, Markovnikov's addition, and then what happens? This will change to your ketoenol tautomerism, so will exit and an aldehyde. Another case where ketone is formed, same reagents, CH3, C double bond OR. Okay, next hydroboration. Hydroboration, remember, terminal alkynes give rise to aldehydes, whereas non-terminal alkynes give rise to ketones. I'll just give you a simple example. You have CH3C triple bond C, CH3 in the presence of hydroboration, that is bovine, in presence of THF tetrahydrofuran, you get CH3C double bond CH, CH3 thrice. This is the organoboron compound, which if you now, this is hydroboration and then followed by oxidation, so hydroboration oxidation, So this is first hydroboration, then you do oxidation using hydrogen peroxide, then you get CH3, C, OH, double bond, CH, CH3. Okay, this will exist in equilibrium with the tautomeric form, which is the keto form, which is more stable than the enol form in the keto-enol tautomerism. Okay, so that was some alkanes, alkynes and alcohols. Next we go to another group of compound, that is the aldehydes ketones, which is formed from a particular reagent, which is none other than a very famous reagent. If you can remember, it's a Grignard reagent. So from Grignard reagent, let me write down first, then I'll explain. This is plus delta minus delta charge, and here this contains negative charge, this negative and this positive, which you know in Grignard reagent. So, Grignard reagent, you treat it with HCN, hydrocyanic acid, and what happens? This being negatively charged, positively charged, you know. So this goes and attacks in this carbon atom, giving rise to this R. This gets shifted here, and MgI gets attacked to partially negative charged nitrogen atom. Okay, so basically what happened? This R goes and attacks, and this negative charge goes here, this MgI goes and sits here with this. Now if you hydrolyze it, so nitrogen having negative charge, hydrogen gets added to get this imine, this your imine, and you get MgOHI. If you hydrolyze it, this gets splitted, getting double bond O plus an ammonia. Okay, let's take some example. I'm taking HCN. So this is what you get is an aldehyde. Now how to produce a ketone? Instead of HCN, if I use RCN, I'll get rise to a ketone. Okay, so HCN, aldehydes, RCN, ketones. So I'm using this compound. So what you will get as the product? H, so you'll have this C is there, double bond O, plus these groups get attached, this plus ammonia, plus Mg, OH, Br. Instead of HCN, if I use RCN plus Grignard reagent with this as the alkyl group, you have R, C double bond O, so this is your ketone.